let's compute n plus 1 derivative of this error, the distance between the actual function and the estimate. Right, let's find the n plus 1 derivative, so which is n plus 1 derivative x is f n plus 1 derivative minus t n plus 1 derivative. So you know that this this one is the nth order polynomial because of that. So when you differentiate n plus 1 times, this becomes what? This becomes 0, right? So this becomes 0. So we end up with having n plus 1 derivative of the error function is same with fn plus 1 of x, right? So what we do now, so try to bound this one here. So we try to at least try to bound this function, the error. So let's do that. So we try to bound this error. This is the error. So we try to bound so this one is same with the modulus of f of n plus 1 x. So we are going to find a bound for this. Right, so actually we are not trying to bound this n plus 1 derivative. We are trying to find a bound for this function, right? Keep that in mind, right? So let's erase this one. This one is incorrect, right? So we know that f is an element in Cn plus 1 function set, right? That means f is the n plus 1 differentiable continuous. N plus 1, you can take n plus 1 differential a derivative of f. So therefore we can say, so this one is, suppose this one is bounded, n plus 1 derivative, f n plus 1 derivative is bounded over the interval a and b. So here b is here, some value here. So you can find the maximum, a bound for the n plus 1 derivative of f. So suppose this one is bounded over this interval here, right? Then what do you have? Then what can you say about this? We know that n plus 1 derivative of f is same with the n plus 1 derivative of the error term. So this one is same with r n plus 1 derivative of x. So now we are going to integrate this one over this interval. No, over this interval, right? Let's integrate that. So r modulus of r n plus 1 of x less than or equal m. Let's consider from here this one. So m times the integral dx plus c. So this one is same with m x plus c. C is an arbitrary constant, right? You have to find that constant using your information. Using the information, we can find that, because right, you can find that. So this one is bigger than. So you shift this, when you shift this modulus sign, so that means you take this integral sign inside of the modulus. When you do that one, so this integral is smaller than. So what we did here was you take this integral inside of this modulus sign. When you do that, so this one is less than or equal to this, right? You can show that. So we showed this one in PM2001 course. So this one is true, right? So this one is easy to derive. So when you integrate the n plus 1 derivative, you get, what do you get? Nth derivative of x less than or equal mx plus c. So using this data, using this property here, so you can plug this number into that equation to find arbitrary constant c. So let's plug a into the inequality. So when you plug a into the inequality, this becomes 0. So 0 less than ma plus c. So this means I take this term to other side, then that term becomes negative ma, right? There's this. Yep. All right. Minus ma is the bound. So we have a constraint for c. So if you want to find the least upper bound, you have to find the minimum number of c. So you can choose any number which is bigger than negative m times a. So to find the bound, I find c is equal minus ma. Then so now I sub this one into here, then it gives n nth derivative of the error term is less than or equal to mx minus a. Now you can integrate this again. So finally, so you can integrate this one. When you integrate this one, this becomes n minus 1 derivative, right? So this one becomes n m x minus a to the power 2 over 2, right, plus again a constant. So you can evaluate that constant. So when you sub that one, so this thing, so when you plug a into the inequality, so you get this condition, right? So I picked the minimum value of c. So this is the constraint for c. I pick the minimum one, then n minus 1 derivative x is equal to m x minus a to the power squared plus, and here you can see the pattern. So the Rn of x would be less than or equal to m x to the x minus a, this distance, to the power n. So here look at this. So here you have n, and look at the exponent of this is 1, and when you differentiate this, when you integrate this, this becomes n minus 1, this is squared. If you have n minus n, this should be so if you have n minus 1 here you have n squared. So if you have n minus n, this should be n plus 1, n plus 1, n plus 1 divided by factorial n plus 1. So this is the bound. So look at this, we get this property here. So our error function is less than or equal to m is the bound for this n plus 1 derivative of f, right, over this interval, m over factorial n plus 1 times this factor here. So we found a bound for this error function. So using that error bound, you can say, this function, our approximated nth Taylor polynomial, is approximately equal to f with this error bound. We can evaluate that error bound over this interval, and we can give the interval, right, including this point. So we know that this Taylor expansion is centered or around at a. So including a, we can give an interval, right? So over that interval, so we can say this function, this Taylor approximation, is approximately equal to this with this error bound over the interval, over that interval, right? So I hope you understood this one, what we are going to do. So if your function is finitely many differentiable, you cannot find the Taylor expansion, but you can find the nth order finite number, this polynomial, Taylor polynomial, finite. Now here there are finitely many terms. The highest degree of highest order is n, so this is called nth order polynomial, Taylor polynomial, right? But So this is an approximation to this function, right? When you express, so as I said earlier, if you find some approximation, so you have to measure the error. So this is the exact function and this is the approximation. So distance between f and t is the error. So you can get an so you can bound this error, right? You can find the bound for this error over an interval including this point as well, right? So I hope you understood this one very clearly now, right?